The next lesson we're going to discuss is A.2, which is polynomials and factoring. Give us a little bit of a review over factoring. This is going to be on page 802 in your books if you would like to follow along. So first thing we're going to talk about is adding and subtracting polynomials together. To add or subtract polynomials, you combine the like terms. Okay, remember, like terms are terms of the polynomial that have the same variable raised to the same power. So if we take a look at an example, we have 4x cubed minus 2x plus 7x cubed plus 3x squared minus 4x. So if we're going to add these two polynomials together, first we're going to find our like terms. So our highest degree power is a x cubed, so we have a 4x cubed and a 7x cubed. So if we add those together, 4 plus 7, we have 11x cubed. Next, we're going to find the next highest degree. The next highest degree, if we look, is an x squared, and that is the only term we have. So it becomes plus 3x squared. We continue this pattern. The next term we have is an x to the first. It's the only one, so it's minus 2x minus 4. So adding or subtracting, we're combining like terms. So using that same example, now if we want to subtract these two polynomials, easiest thing to do if we have a subtraction problem, make it an addition problem. And we can do that by changing the subtraction to an addition and changing the sign on every term inside the polynomial that follows. So this would become a negative 7x cubed, a negative 3x squared, and a positive 4. So now we do the same thing we just did in the last problem. We have 4x cubed plus a negative 7x cubed would become negative 3x cubed. We have a negative 3x squared, so minus 3x squared minus 2x plus 4. So, adding or subtracting polynomials, combine like terms. If it's a subtraction problem, you can change it to an addition problem to make it a little easier to work with. Now we're going to talk about multiplying polynomials. Okay, we can use the FOIL method to multiply two binomials. Remember, binomial means bi means two, nomial means terms. So they have two terms. Multiplying those together, we can use the FOIL method. If we have polynomials that aren't binomials, we have to use a form of the distributive property. So basically, we have to multiply each term of one polynomial by every term of the other polynomial. So now we're going to look at an example of multiplying two polynomials together that are not binomials. So in this case, we cannot use the FOIL method. We have x squared minus 4x plus 3 times x squared plus 4x plus 5. So remember, look at that last definition about the process we have to use. We have to take each term inside our first polynomial, multiply it by the whole other polynomial. So if we look, we're going to take x squared, which is our first term in the first polynomial, and we're going to multiply that by the whole second polynomial. Same thing with the second term. Our second term in the first polynomial is negative 4x. We're going to multiply that by the whole second polynomial. Same thing with our third term in our first polynomial, which is 3. Multiply that by the whole second polynomial. So if we take x squared times x squared, we get x to the fourth. X squared times 4x is 4x cubed. X squared times 5 is 5x squared. Now we just have to use that distributive property. If we continue that pattern and simplify, we get 9 terms. Now we're going to have to simplify, combine these like terms to get our end polynomial. So if we start going through this process, first term we have is an x to the fourth. That is the only x to the fourth term we have. So we start with x to the fourth. Now we're going to look at the x cubed terms. We have a positive 4x cubed and a negative 4x cubed. Those simply cancel each other out. If we look, there's no other x cubed terms, so in our end result, we're not going to have an x cubed term. Now we're going to look. We have a 5x squared and negative 16x squared and a positive 3x. So 5 minus 16 is negative 11. Negative 11 plus 3 is negative 8x squared. Now we look at our x terms. We have a negative 20x plus 12x, which is minus 8x plus 15. So our end result for our polynomial is 4x, or x to the fourth minus 8x squared minus 8x plus 15. We have a few special binomial products. This is going to be on page 803 in your books. It might benefit you to look at that table. It'll maybe make a little more sense, or it's a little neater than what I can put on here. But we have 5 different special binomial products. The product of a sum and a difference, the square of a sum, and the square of a difference. Those are the first 3 which you can recognize, but basically those ones you can use the FOIL method for. The ones we're going to focus on are numbers 4 and 5, the cube of a sum and the cube of a difference. We could use the FOIL method to simplify these out, but we would have to use the FOIL method 2 times for each one. So if we can recognize this pattern and use this pattern, it's going to make the process a little quicker. Okay, so I would copy down these in your notes, and it might benefit you to use the table on page 803 to use that. Alright, now we're going to look at an example of a cube of a difference. So that means we're subtracting our 2 inside terms, and they're raised to the 3rd power, cube of a difference. So using that formula, it's u cubed minus 3u squared times v plus 3u v squared minus v cubed. Our u value is 2x, our v value is 3y, so we basically just have to plug these into the formula. So that means we have 2x cubed minus 3 times 2x times 3y, and this was squared, plus 3 times 2x times 3y squared, and then finally minus 3y cubed. So now if we simplify these, this first term we have 2x cubed. That cubed gets applied to each factor inside the parentheses. So that means we have to take 2 cubed, which is 8, and then x cubed. Now we need to simplify the second part. We have negative 3 times 2x squared. 2 squared is 4x squared times 3y plus 3 times 2x is going to be a 6x, so we can simplify that a little bit right away. And then 3y cubed, 3 cubed is 9, or 3 squared, excuse me, is 9. So this becomes 9y squared. The last part, 3y cubed minus 27y cubed. So, last step is to simplify. 8x cubed. We have 3 times 4, which is 12. 12 times 3, which is 36. So we have minus 36x squared y. Then we also have a 6x times 9. So 6 times 9 is 54 xy squared minus 27y cubed. So that's how we take the difference of a cube. If we can recognize that pattern and use the formula, we can plug those values in rather than trying to use the FOIL method twice. Factoring is the next example we're going to talk about. You just had a worksheet that covered many factoring patterns, specifically when we had a trinomial with a leading coefficient other than 1. So now we're going to talk about a few other patterns that we have talked about in the past, but it's good to review those. So if we look at part A, we have u cubed times v plus u times v cubed. One of the first things you should do if you're ever trying to factor is look and see what do these terms have in common. So if we look at part A, both these terms have a uv in common. So if we take a uv out of each of these terms, we're going to be left with u squared plus v squared. So if we look at u squared plus v squared, that looks similar to a pattern we talked about in the past, but the only problem is this is addition. If this was a subtraction, then we could simplify this a little more, but since it's addition, this is as far as we can go. So take out what they have in common. In part B, we have 25x squared minus 36. This is our difference of squares. We need to do a little rewriting with our first term, 25x squared, so that we can easily see how this becomes a difference of squares. So we know 25 is the same as 5 squared, and we still have our x squared, minus 36 is the same as 6 squared. So in this first term, if we have 5 squared times x squared, we can rewrite that as 5x squared minus 6 squared. So now we can see we have two terms that are squared and we're subtracting them. So this is our difference of squares. This factors into 5x minus 6 times 5x plus 6. So the difference of two squares, we've talked about that in the past. We have to go a little more in depth now about how we can rewrite those terms so we can easily identify how it is a difference of squares. In part C, we have 8x cubed plus 27. This is the sum of two cubes. Again, we need to rewrite this so that we can recognize what those two cubes are. So 8 is the same as 2 cubed. X cubed plus 27 is the same as 3 cubed. So we need to practice rewriting these numbers as some number cubed. Again, we can rewrite this as 2x cubed plus 3 cubed. So now you can see we have two things, 2x and 3, that are both cubed, and we're adding them together. So last year in Algebra 2, we talked about all these patterns. If we can start remembering these patterns, it's going to make this process a lot quicker. So we have basically our a value of 2x and our b value of 3. So in our first factor, we're simply adding those two terms. So we have 2x plus 3. Now in the second part, we need to take 2x squared then we need to subtract from that 2 times our a value of 2x times our b value of 3. And then the last part is we have to add 3 squared. Now it's just a bunch of simplifying. So in the first term we have 2x plus 3. In the second part, if we square 2x, that becomes 4x squared. 2 times 2x is 4x. 4x times 3 is minus 12x, and then 3 squared is plus 9. So if we take that cube and try to factor that down, it becomes 2x plus 3 times the quantity 4x squared minus 12x plus 9. And you're probably asking, how is this beneficial? We got something that looks more complicated than what we start with. Well, if we're trying to solve these, one method is factoring. So now I could set this first factor equal to 0 if we're trying to solve. And now I could look at the second factor. That's just a quadratic function. We could try to factor that if we're looking to solve for those x values. We can use the quadratic formula. We could graph it. Many different things we can use if we break this down into functions, polynomials that we are more familiar with. The last example, part D, we have 3x cubed plus x squared minus 6x minus 2. This one's different than the other ones we've been working with because there are 4 terms instead of 2 or 3. And you're probably confused, having no idea how we can factor this. As soon as I write something down, you'll probably remember one of the patterns we talked about last year was factoring by grouping. And we use this method if we have 4 terms. It's called factoring by grouping because we're going to group the first 2 terms together and the last 2 terms together. When we group the first 2 terms, 3x cubed plus x squared, we're looking, what do those 2 have in common? Well, they have a factor of x squared in common, which we can take and put out in front. If we do that, we're left with 3x plus 1. Now we're going to do the same thing in the second, or the last 2 terms. Negative 6x minus 2, what do those have in common? They have a factor of negative 2 in common. So if we take that out, we're left with 3x plus 1. If you're starting to remember this pattern from last year, when we look, one way we can check, those 2 terms need to be the same value, 3x plus 1. And if that's the case, that becomes one of our factors, 3x plus 1. Now we need to look at what we took out in front, x squared minus 2, and we combine those together to make our other factor. So this factors into 3x plus 1 times x squared minus 2. Okay, and now we're done. That is factoring by grouping. That basically concludes A.2. That is all I'm going to require you to remember from this lesson. Okay, this last part here, you can choose to watch this or not. Some of you will probably find this a little interesting. Having a better understanding of Pascal's triangle may help you more on an ACT. They might have questions relating to that. So I'm just going to go through how we can use Pascal's triangle because it becomes important when we're dealing with multiplying binomials together. Alright, so some of you may find this interesting. If you want to get started on the homework, that's fine. If you want to take a couple minutes, try and understand what Pascal's triangle is, how it benefits us, by all means watch this last part. Alright, Pascal's triangle. The thing with Pascal's triangle is broken into many rows. This is actually row 0. This is row 1. Here's row 2. And this pattern continues on, row 3 and row 4. There's many unique, interesting qualities regarding Pascal's triangle. For instance, if I take 11 and raise that to the 0 power, that is equal to 1. If I take 11 to the first power, that is equal to 11, 1, 1. 11 to the second power is equal to 121. You can probably understand, assume, guess, 11 to the third power is equal to 1,331. Go ahead, and that pattern continues on as we go down the rows. Also, how we can look at the rows, inside the triangle itself, if I take 1 plus 1, these two numbers added together, they equal 2. If I would take 1 plus 2, they equal 3. If I take 1 plus 3, they equal 4. 3 plus 3 equals 6. 6 plus 4 is equal to 10. And that pattern continues on as well. Okay, so we already start to see a couple patterns dealing with Pascal's triangle. So if we use that pattern and tried to make the next row, this was row 5, so if we wanted to try to make row 6, using the patterns we just talked about above, we always start with a 1. 1 plus 5 is 6. 5 plus 10 is 15. 10 and 10 is 20. 10 and 5 is 15. 5 and 1 is 6, and we end it with a 1. Okay, so that would be the 6th row of Pascal's triangle. That would be the same as 11 to the 6th power. Now, if you type 11 to the 6th power into your calculator, these will not be the numbers that pop in there. Okay, you could come ask me separately how that works, and I think it'll make a little more sense what we have to do to make that work. What we're going to use Pascal's triangle for is binomial multiplication. So remember, we had the sum of a cube. That was one of the ones I told you to write down, u plus v cubed. Okay, you should remember what that's equal to. That is equal to u cubed plus 3u squared v plus 3uv squared plus v cubed. So how Pascal's triangle applies to this case. If we look at our coefficients, in front of our first term we have a 1, 3, 3, and a 1. So our coefficients are 1, 3, 3, 1. Our power was 3. So if we look at the third row, our coefficients are found in Pascal's triangle. 1, 3, 3, 1. So anytime we're taking a binomial, anytime we're taking two terms and raising them to some power, if we know the power we're going to, say the 7th power, if I go down to the 7th row in Pascal's triangle, I know what my coefficients need to be in front of each term. Okay, and that becomes beneficial because we'll talk about in class, there's also something we can start to recognize that happens on the degrees of these terms. For instance, my u cubed, so my u variable started with a 3. Notice in my second term, it was a 2. In my last term, or my second to last term, excuse me, it was a 1. And in the last term, there was nothing because it was to the 0 power. So each time it decreased by 1. Well, if you look at the v exponent, or excuse me, the v variable, in the first one it's not there because it was a value of 0. In the second term, that exponent is 1. The third term, that exponent is 2. And the last term, that exponent is 3. So each time, the degree on the v variable increased by 1. Okay, so there's many interesting patterns that we can start to use to help make this binomial multiplication much easier. Okay, so if you have questions over any of this, come talk to me and we can go through it a little more in depth on how some of these tricks work.